So, hello everyone, this is lecture 19 for the solid state physics. In the last lecture, we studied about the modes of vibrations in the lattice vibrations, and we completed that. You can check the last lecture. And in the extension of this specific heat is also part of lattice vibrations, means the thermal properties are affected by the vibrations inside the solid. So, we will study the specific heat of solid now. So first, let's see the definition. That is heat capacity. It is nothing but amount of heat required to raise the temperature of mass m by 1 degree. That is normal heat capacity. Okay, for any m mass, the amount of heat required to increase the temperature by 1 Kelvin, that is specific. That is heat capacity. And what about specific heat? So you guys know that for unit mass, the amount of heat required to increase the temperature by 1 degree, that will be specific heat. And that unit mass can be 1 Kelvin, 1 kilogram, or 1 mole. That can be anything. Okay, for 1 mole, that will be molar specific heat capacity. Means just see here, if this is m mass, then the amount of heat required Q to raise this temperature 300 to 301, that will be heat capacity for this. And if this material is 1 mole, then the amount of heat required will be specific heat, or the molar specific heat. Okay, so C can be defined for the 1 mole, that is dQ by dt. Okay, here Q is amount of heat required to, and dt is change in temperature. Okay, so dQ is amount of heat supplied to change temperature of unit mass from T to T plus dt. Okay, the change will be dt then. So in thermodynamics, we study that first law of thermodynamics says that dQ equal to du plus p dV. That is, the amount of heat given to a system will affect its internal energy and the work done. Means the amount of heat you will provide to the system. Let's say this is a piston and this is gas. If you heat, if you provide the heat to the system, then what happens? The amount of heat will be gone to raise its internal energy and some work done, means by increasing the volume, this piston go up, so its internal energy will increase and its volume will increase, so some amount of work is done and some amount of internal energy is increased due to this dq. Okay, I hope you get the point. Okay, so du is change in internal energy and pdv is work done. Now you will study this thing more in the thermodynamics. Here just I am giving you the idea. I already started a lecture for the thermodynamics, so go watch that from starting, that is thermal physics. Okay, so let's continue. So now we have specific heat capacity at two conditions we have. Okay, for the specific heat, that is at the constant volume or at the constant pressure. So what happened to the specific heat at constant volume? So we know that specific heat is dQ by dt for 1 mole. So from this equation we can see that at constant volume this dV will be 0 and del Q will be du. So Cv will be nothing but du by dt. Here it is capital D, that is temperature. And at constant pressure this is nothing but just dQ by dt will be du by dt, p dV by dt. So this will be Cp, this whole, and this will be Cv. If you know the internal energy, then you can calculate Cv. Then using Mayer's relation, that is Cp minus Cv equal to R, you can also calculate Cp, but from here also you can calculate Cp by observing the change in volume. Okay, with the pressure, constant pressure. So let's see more about this. First, volume is constant, C. We are providing heat to the system and keeping the volume constant. So what you observe that if the volume is not increasing and you are providing heat, then what happen? This movement inside this particle will increase. They will be more rapid. So that will lead to the increase in its internal energy, that is du. So dq will be directly proportional to du. As dq increase, du will increase. Okay, and Cv is nothing but du by dt. Okay, now for the constant pressure, we derived this equation, Cp equal to du by dt plus P dV by dt. Now when you provide heat to the system, so that will increase its internal energy and increase its volume, because if you keep the pressure constant, then it has to expand to keep the pressure constant. If you provide the heat, then pressure will be constant only if it expand, otherwise the pressure gonna increase in this system. So if it expand, then pressure can be keep constant. That's why it expand and the work is done on this system. So Cp is du by dt plus P dV by dt. So by this observation, what you see here, no work done is going to done, so whole heat will be converted into internal energy. So and here it is gone in some work done also, and we know that temperature is directly proportional to internal energy only. So the amount of heat required here will be less as compared to here, because here the work is also done, but here all heat is going to increase its internal energy or its temperature. So the amount of heat required to raise the temperature by 1 degree will be less here and more here. Okay, I hope you get the point. From these equations we can find that this sum is more and this is small, so this amount of extra energy is required in the Cp case. So that's why Cp is greater than Cv, we can write this. Okay, and you will get the proof in thermodynamics, that is Cp minus Cv equal to R. Okay, and what is temperature? Temperature is nothing but it is a measure of average kinetic energy, or it is a measure of average internal energy. So temperature is nothing but the measurement of its internal energy of a system. Okay, or the basic definition, that is degree of freedom or the degree of heatness and coldness. So we'll study more about it. Now in solid, I hope you get this whole thing. In solid, at low temperature the volume of the solid doesn't change. So in the gases we can consider the constant volume, constant pressure, but what happens in solid, we say that volume is not changing, so Cp is mostly equal to Cv, and we get this relation, that is Cv equal to du by dt. Okay, because we know that inside a solid there is very less movement, so pressure and volume is almost same, means it remain constant, doesn't change. So Cv will be du by dt for the solids, okay, at very low temperature or a low temperature normal. Okay, so this will be this. Now there is in this classical theory we have this Dulong-Pettit law, which says that each atom is an oscillator. We already seen this in lattice vibration. Each atom is an oscillator, that is classical oscillator. So what happened in the classical theory? So if this is a solid, so these are the atoms, so each atom is a oscillator, that is oscillating at its position. Okay, so then each particle is oscillating, then it will have kinetic energy and potential energy, and both are assumed to be equal. Both are the average value of both of them are assumed to be equal, and one component will have energy this. We proved this in the equipartition law. Okay, that is you will study in the thermodynamics, so go must watch that videos in the thermal physics. Okay, that will help you very much. So these energies will be average will be equal, and each will be half kT. So for one mode, for 1 degree of freedom, and this we know that average energy will be half kT. Half kT will give you kT. Okay, here k is nothing but the Boltzmann constant. So in one dimension it is this. If it is moving in 3 dimensions, that will be 3 kT for one molecule or one atom. Okay, so I hope you getting this point. In 3D the average energy is nothing but 3 kT, that is average energy per particle. Okay, now in 1 mole of solid, that is for one particle. Now in 1 mole, that is Avogadro number 6.02 into 10 to the power 23 atoms in 1 mole. So E will be NaE, so that will give you this. NaKV will give you R, that is gas constant 3 RT. Okay, and this is nothing but internal energy of a system. Now to find the specific heat, that is Cv for the solid, you know that what to do, du by dt. So differentiate it with respect to temperature, you will get 3R, and R is 8 point something, so it will give you 25 joule per Kelvin. Okay, or per mole inverse, you can say per mole. So what you see here, this is just mathematical. What we observe from this, It says that Cv is equal to 25 joule per Kelvin. That is for all solids. It is independent of the nature of the solid, what it is, and it will remain constant for everything in the classical theory. Okay, this will remain same for every solid. Okay, and it is independent of temperature also, that at what temperature you are giving this energy, it will raise 1 degree temperature. Means specific heat is temperature independent from this theory. And you will see that there is this solid at 300 Kelvin and this solid at 310 Kelvin. Now to increase this temperature by 1 degree and this temperature by 1 degree, you will need the same energy, 25 joule for 1 mole. So it will be same and it is independent of the temperature of that system. Okay, so this is what classical theory says. But when we see the experimental values, so this plot is given by the experiments. So let me make it easy for you. This is 3R value Cv and this is temperature. Now this line shows 3R specific heat capacity. So for all solids this should be a straight line for all solids. But what we observe actually in the experiment, that when we go down, the temperature is decreasing this side. So we see that at low temperature the specific heat start to decrease for every solid. For every solid specific heat start to decrease. Means at very low temperature very small amount of heat required to raise the temperature by 1 degree, and it increases with increase in temperature, and at some temperature they all becomes constant and reaches to 3R, saturates to 3R. So now here classical theory fails, because at low temperature you can't define that it should be 3R. It is varying with temperature. Means it is not independent of temperature at low values. So you can see that it is not independent of temperature. And not just this, we can see that high temperature is also different for different elements. Means we can say that at high temperature all solids will approach to 3R, but for lead this high temperature is here, and for copper it is not that high temperature. For copper it is low. This will lie somewhere here, and at this point also this is different for aluminium, also for carbon here. So high temperature is also not fixed for different elements. Means it will vary element to element, the high temperature. Okay, so we can't define the high temperature and what is low temperature, and it is dependency, the specific heat dependency on temperature. Okay, so this was the very big failure for the classical theory. Okay, so we can say the failure, it is unable to explain the temperature dependence at low temperature, although at high temperature Cv equal to 3R. So high temperature is different for different elements. Now because of this thing, here comes the quantum theory. That is that there was two theory was given to explain this. First was Einstein theory of specific heat, and that is second one is Debye theory of specific heat. Okay, we will study both these theories, and we'll see that if they will be able to describe this plot or explain this plot and the temperature dependence. Okay, so first let's see the Einstein theory of specific heat. Now what there are some assumptions taken by the Einstein first. So what assumptions are? So we take some simple things to explain something. Okay, so Einstein also assume some simple statements, that is atoms in solids are behaving as quantum oscillators and not as classical oscillators. So previously the Dulong-Petit law, we see that atoms are supposed to be classical oscillator, but Einstein said that they are not classical oscillators, they are quantum oscillators. Means now we are considering the quantum nature in the Einstein theory. Second one is each oscillator oscillating independently from each other. Now, well, I know you will think that this is wrong. Well, yes, this is wrong, but here Einstein just taken the simple assumptions. Okay, so he take this like each oscillator is independent of other oscillators. Okay, each atoms is oscillating independently from others, no coupling around. Third one was one atom is equivalent to 3 independent harmonic oscillators. So one atom is equivalent to 3 independent harmonic oscillators, means they are in 3 direction, means one atom can oscillate in 3 axis. So that's why 3 independent harmonic oscillators are possible with one atom. A solid having n atoms is equivalent to 3n one-dimensional harmonic oscillators. So for one it is 3, for n atoms that will be 3n one-dimensional harmonic oscillators. Okay. Now how we get this point, means in one dimension there are n, in second one dimension there are n, then in third dimension that is n, so total will be 3n one dimensional harmonic oscillator you will have. Fourth assumption was each oscillator oscillating with some same frequency due to identical environment. So each oscillator inside that solid will be oscillating at the same frequency due to identical environment. First one was, since each oscillator is a quantum oscillator, it will possess different energy spectrum and not continuous energy spectrum like classical oscillators. So what we study in the classical theory, that this one oscillator can possess all possible values of energies, means this will be continuous. Okay, the energy for this atom will be continuous. But in the quantum we see that energy is not continuous, that is discrete. Okay, so if we consider the quantum nature, so we will take the discrete energies. So since each oscillator is a quantum oscillator, it will possess different energy spectrum and not continuous energy spectrum like classical oscillator, and energy will be n plus 1 by 2 h cut omega. Okay, for the each mode. Okay, means this will be the values, means first energy will be possible h cut omega by 2, second will be possible 3 by 2 h cut omega or 5 by 2 h cut omega. So these will values will be possible. Okay, so these discrete energy will be possible. No meanwhile energy can be possessed by the oscillator. Sixth one was, since each atom are at distinct locations inside solid, therefore the atomic vibrations follows Maxwell-Boltzmann distribution of energy. Now we see that because of atoms at distinct location inside the solid, they will follow the atomic vibration of the solids or the atoms will follow the Maxwell-Boltzmann distribution of energy. You will study this statistics in the thermodynamics. I will teach you, just carry on with the lectures in the thermal physics. Here we will just take the results. So if there is one atom, so it can oscillate in these discrete energies. So E naught will be h cut omega by 2, possible this energy can be possible, or this energy can be possible. So there are, if n atoms are there inside a solid, and n naught in first state, n1 in this second state, n2 in third state, these are like that. So we can write the average energy for the oscillator, that is, or the system, E naught n naught plus E1 n1. Here n naught is energy with E naught, n1 with n1 number of particles with energy E1, n2 with E2, and this is n1 n naught n1 n2, this is whole particles. This will be the average energy. Okay, so from the Maxwell-Boltzmann distribution law statistics, we know that n1 by n naught will be this, E minus delta E by kt, that is difference between n1 and n naught. This is delta energy between these two. Okay, and if they at nth particle, nth energy level, nn divided by n naught will be E minus En minus E naught by kt. So En minus E naught will be, En is this, n plus 1 by 2 h cut omega, and E naught is h cut by omega, h cut omega by 2. So if you minus from this from this, you will get n h cut omega. So nn by n naught will be E minus n h cut omega by kt. Okay, so from here you can just substitute the values. E naught value, you know that h cut omega by 2, n naught, and n1 can be written in terms of n naught, that is n naught E minus 1 h cut omega by kt. And you can substitute the values for n naught, n1, n2, and from here in the statistics you will see that Maxwell-Boltzmann statistics, you will get this result for the average energy. You can try to solve this by yourself also, otherwise I will tell you in the thermodynamics how to do this. Here just you need to remember this result. Average energy will be this. This can be solved to this, h cut omega by 2 plus h cut omega divided by E h cut omega by kt minus 1. Okay, here k is nothing but Boltzmann constant, T is temperature, omega is frequency, h cut is Planck's constant, means h is Planck's constant, h by 2y can be written as h cut. Okay, now this is nothing but average energy per oscillator. Okay, now let's see, this energy nothing but internal energy also. So we will try to find the specific heat with this relation, and we will see that if this relation is explaining that plot or not. Okay, so that is the map we are going to follow. So in 1 mole of solid, n equal to Na. Okay, this is the amount of atoms in 1 mole. So if this is for 1 oscillator energy, then for in 1 mole, that is 3n, means if Na particles are there, so this will give you 3Na. Okay, so from here you can see that we already discussed this, that 3n oscillators are possible. So if particles are Na, then 3Na oscillators are possible, and each oscillator having this energy, so just multiply with 3Na. So half h cut omega will multiply with 3Na, and here 3Na, this is multiplied. Okay, I hope you get this, how we get this result. Just multiply 3Na in this whole equation. Now this h cut omega by k is nothing but, this is called Einstein temperature. Einstein temperature we call it, theta E, and here omega is nothing but Einstein's frequency. Okay, we call this omega as Einstein frequency. So we just let's substitute this, or we can write this equation like this: 3 by 2 Na h cut omega 3 Na h cut omega E theta E by t minus 1. So we can write this like, but we will use this relation, just the same one. So you know that to find the specific heat, what you need to do is just du by dt for Cv, du by dt. So differentiate this whole equation with respect to temperature. So what you will get, this term will turn out to be 0, and when you differentiate this, it is 1 upon x, so it will give you minus 1 upon x square, that is minus 1 upon this whole square. Then by chain rule you will differentiate this, so this is e to the power x, that will give you e to the power x. Then 1 upon x will give you minus h cut omega by kt square. Okay, and what else you will get, that is h cut omega by k, means e की power x will give you this, and this whole term will give you h cut omega by kt square. Then minus 1 will be differentiated to 0. So this is nothing but just a simple differentiation. Just focus and you will get this result. Okay, now we multiply this k by k separately. Okay, k by k, so just multiply k with this will become kt whole square, and take this h cut omega here, that will be h cut omega square. So we can write this like h cut omega by kt ka whole square, and this 1k will go to Na, that will Na k will give you r, so this will be 3r, and we will get this result, minus minus will turn out to be plus e to the power h cut omega by kt divided by this result. So we can write this equation like this. This is simple math. Now we get this expression for Cv. Now we need to simplify this expression. Okay, so there are two cases. Let's see. First, at the high temperature is very high, so what this result will be. So at high temperature we can see that this h cut omega by k is theta E, so theta is very less than T. Einstein temperature से बहुत ज़्यादा temperature है, capital T. T is very high than Einstein temperature. So just assume this h cut omega by kt as x. So e की power x, e to the power x minus 1, e to the power x minus 1. So this h cut omega by kt is very small because of high temperature. Okay, so this x is less than equal to 1, less than 1. So from the relation we know that if we have this type of thing, e to the power x minus 1 and x is less than 1, then you know the expansion of e की power x is nothing but 1 plus x square plus x cube. So the higher order terms will be neglected. Then 1 plus x minus 1, so 1 will cancel out, this whole term will be equal to x. Whole term will be x, means this middle terms will be neglected because of higher terms. So 1 plus x minus 1 will cancel out and x will remain. So this term will be approximately equal to x, and e to the power x, because of x is very small, we see that at high temperature x will be very small, so e to the power x will tends to 1. Okay, so just take these values and substitute. There is nothing but e to the power x minus 1, it will turn out to be h cut omega by kt, that is x, and this is e to the power x, that will turn out to be 1. So what we will get? We will get this result, and they will be cancelled out, and Cv will turn out to be 3R. So this is valid, means at high temperature we are getting the value that is 3R, that is equal to the means what we are getting in the classical theory, that is same, and also the practical results, we experimental values get the same result. So at high temperature it is okay. Now we need to explain at the low temperature. At low temperature what happen? At low temperature this h cut omega by k is very high than t, means now t is less than theta e, okay, means now Einstein temperature is higher. So when t is very less than, then this term will be very large, then e to the power x minus 1 will be approximately equal to e to the power x, because 1 can be neglected because this term is very high and exponential also. So we can write this as Cv 3R h cut omega by kt ka whole square e to the power x minus e to the power x square. Okay, this x is nothing but h cut omega by kt. Okay, so this will give you what? This will give you this relation you will get. Now from here you can see that Cv is directly proportional to e to the power minus h cut omega by kt. Okay, this t is nothing as compared to this exponential term, that's why we are plotting this exponential term only. Okay, so this Cv is proportional to this term. Now when we plotted this, as I already told you, theta is h cut omega by k, and that is Einstein temperature, and omega is here Einstein frequency. So when you plotted this, what you will get? You will get this down one curve, this curve you will get, and this is very much correct, means we are now getting the temperature dependence. That was the success of this Einstein theory for the specific heat, that we are getting the temperature dependence, but still it's not what actual graph is, means it is not proportional to t to the power 3, it is in exponential terms. So we are getting something but not exact result we are getting. So that was the failure, that we are not getting the exact result, but we are getting something, means temperature dependence, and it is more closer to the actual curve. So that was the success. In 1D monoatomic solid, we studied that we find out this frequency for one atom, that was root 4 beta by m sin k by 2, and this is nothing but maximum frequency, and we call this frequency as Einstein frequency. So this is omega e. Okay, here beta is nothing but fourth constant. You will see in the lattice vibration, you can know what is beta. So what was success? It saw temperature dependence. And what was the failure? Its actual behavior at low temperature is not t to the power 3 proportionality, means it is, we are getting exponential proportionality. This was the failure. And what is the reason behind this? This is because of oversimplified assumptions that atoms are oscillating independently from each other, means we taken this assumption that they are oscillating independently, means in reality atoms are coupled together, and if one atom is displaced, it will displace the neighboring atom also, means the oscillation of one atom affect the second one or the previous one. So that was the assumptions we taken, means very simplified assumptions we take. That's why we are getting these some failure, okay, and some success. So in the next lecture we will study the Debye theory. So today we reached somewhere, now we will reach the exact value in the next one. Okay, so stay connected. Thank you.